Hello everyone and welcome back to FatalSec. I am starting a brand new series focused on both Android and iOS where we will be tackling the reversing challenges from 8K SEC. For those who don't know, 8K SEC has recently launched some really exciting labs covering Android, iOS and even native ARM challenges. Getting started is super simple. Just sign up and log into your account. Once logged in, you can click on any of these challenges. Since we are starting with iOS, let's click on iOS application challenges. Now here you will see a brief description about what these challenges are all about. Let's just click on continue, and here at the top you will find a kind of a readme guide explaining how to set up things, what you will learn, how to set up your environment and everything. I recommend going through that on your own to get familiar with the basics. After that, you will see the first challenge, which is called Frida in the middle. Let's click on the challenge overview, and here you will basically see the description about the challenge, what we have to do and what are the restrictions or basically the rules which we have to keep in mind while reversing or attacking this application. So here it basically says, welcome to Frida in the middle, a Swift-based iOS application that's extremely sensitive to uninvited interference. It comes pre-cubed with active runtime tamper detection that watches for signs of Frida. Alright, so by reading this description, we know now that this application has some kind of Frida detection implemented in this. And it even gives us a hint about what kind of detections or what kind of detection mechanisms might be implemented. For example, the application might be looking for suspicious ports, injected device libs, or unauthorized hooks. Alright, let's see what we have to do now. So we have to keep the app running while Frida is attached and intercept the argument passed to this dummy function to extract the flag. Okay, so all we have to do is somehow attach a hook to this dummy function whose first argument is a flag which we have to extract. Now the most important thing is, so using static reverse engineering is not allowed. Okay, you must rely on dynamic analysis to retrieve the flag during execution. Okay, this means that simply by doing static analysis it's not allowed to extract or capture the flag. Okay, cool. And here at the end we have the download button which will download the IPA file. I already have it downloaded, which is there under documents, trainings, iOS 8ksec challenges directory. So here I already have the IPA file. Now in order to install it, there are a couple of options. You can use a tool which is called sideloadly. This basically allows you to sideload an application onto a jailbroken iOS device. So here it's showing me the device which is connected to my Mac, which you can also see over here. Alright. Now to sideload this IPA file, all I have to do is click on this IPA logo. Go to the directory where this IPA file is located, which is under trainings 8K20sec, Frida in the middle, and click open. Okay, here before starting you have to mention your Apple ID and then click on start. And here you can see that it's doing some processing on it, trying to install it, and now there you see it's currently being installed and it's done. Okay, so that's how you can sideload an IPA file on a jailbroken iOS device. Now this tool is not required anymore. Let me just close it. And before we dive in, I want to point out a couple of things. Firstly, we will be working on a jailbroken device, specifically jailbroken using root hide dopamine. The nice thing about the root hide variant is that it helps bypass most jailbreak detections automatically. So if any of these challenge applications comes with jailbreak detection mechanisms, we won't really have to worry about them. Now there are already plenty of tutorials available that will walk you through jailbreaking your device with root hide dopamine. But if you still run into issues or feel stuck, drop a comment below and I will create a dedicated video on jailbreaking with root hide dopamine. Okay. Second thing is, on my device, I have Frida already installed with Celio Package Manager. So once you jailbreak your device using dopamine, Celio Package Manager will be installed by default, and then all you have to do is go into sources, make sure that you have this Frida repository added over here, and then what you have to do is go to search, click on search for packages and look for Frida. Okay, and make sure that Frida is installed. Okay. Now the thing you have to keep in mind is that once Frida is installed through Celio Package Manager, in the background Frida server starts automatically, which then allows us to attach to any application via Frida client, right? Okay, so now we have pretty much everything we need in order to solve this challenge. So let's launch the app now and observe its behavior. Okay, let me launch it again. So it says that Frida is detected, Frida activity was detected, and then the app is getting killed. From the error message, it is clear that Frida is being detected by the application, and that too because either of the port or injected dylib. However, we have not directly injected any dylib into the application's process so far, so it has to be because of the port. Now, like I mentioned previously, in the background, we have Frida server already running, right? So this detection could be because of that. Now, in order to figure out how exactly the detection mechanism is working inside the application, what we have to do is perform some kind of analysis on the application, right? Which means we will first extract this IPA file and do some quick static analysis. So IPA file is nothing but a zip file. So let me just copy this IPA file and change its extension from IPA to .zip. Okay, and now using unzip command, I can simply extract this IPA. Alright, so now after extracting it, we will get this payload directory. Let's go inside it. So here we have a .app file. So again, this is not a file, but a directory inside which we will get all the resources, artifacts, and everything which is bundled into a IPA package. So let's go inside this directory, list the contents. So here basically I can see two binaries. One is Frida in the middle and another one is Frida in the middle.debug.dylib. This Frida in the middle is the main application's binary, okay, and this .dylib extension means that this is a dynamic framework. So as of now we cannot say in which binary the main logic of the detection is present. So let's just first start with the main application's binary, which is Frida in the middle, and in order to perform a static analysis on it, we have to open it into some kind of disassembler, and this time I am going to use Ghidra, which I already have opened over here, and now all I have to do is click on file and import this binary. So now we have to select first Frida in the middle binary because that's what we are going to analyze. Select file, okay, and now to start analysis we have to simply do a double click. Yes, leave all the checks as it is and click analyze. Okay, so the analysis is now done. Now in the application, we have observed that when Frida was detected, it was throwing a error message which says Frida detected via socket port or something, right? What we can look for inside this binary is the strings section. So let's click on this search menu for strings. Select all blocks, search. Now it will show you all the strings which are present in this Frida in the middle binary. So there are quite a few strings, but I don't see anything which says Frida. Let's just search for Frida string from the filter, and nope. We cannot see the exact string which says Frida is detected, right? However, there is another interesting thing we can see. So you see this at the rate rpath Frida in the middle .debug.dylib. This suggests that this Frida in the middle application's binary is trying to load this dynamic library at some point of time. Let's also quickly see if under import section we can find something useful. One is system B, and these are the default imported functions. Then this is the external dependency Frida in the middle.debug.dylib. Right, so apart from this I cannot find or I cannot see anything interesting in this binary. Let's also under the functions, let's try to see if we can see the dummy function which we want to target. No, okay. Under functions also there is no such function called dummy function which we have to target. So yep, nothing interesting at all in this particular library. So now at this point what we can do is, instead of spending more time understanding what this particular Frida in the middle binary is doing, let's quickly have a look at this Frida in the middle.debug dynamic library. Okay, so let me just close this one, save. Again in Ghidra we have to import this dynamic library to analyze it. Okay, let's just double click on it to start the analysis. Yes, analyze. and it's currently being analyzed. Give it some time for the analysis. All right, so there are some warnings being displayed. Let's just ignore it for now. Oh, all right, so now this dynamic library is disassembled. Again, let's do the same thing. Let's look for the strings, all blocks, search. Yep, there are a lot of strings present in this one compared to the previous binary. Let's search for Frida in this one. Yep, cool. So now we can see some interesting strings which says Frida detected, and after that we can see the exact error message which was being displayed by the application. So now what we can do is, we know that this in this dynamic library, this string is present, which is being displayed when Frida is detected in the application, right? So we can take it as an entry point and try to reverse from this point. So let's see in which function this string is being called. So the idea over here is simple. We will try to figure out the function which is basically trying to detect Frida, and by backtracing this string, eventually it will lead us to the function, because anyhow within that function only, when Frida is detected, this error message is being displayed, right? So everything is connected. Let's double click on it, and it took us to this data section directory where this string is defined. And if we have a look at its cross references, there is only one cross reference which is from Swift UI alert. So let's go over here. Yep, okay. So this Swift UI alert is the function from where I guess this alert dialog is being generated, because over here we can see that it's initializing some Swift text and then a Swift string which says Frida activity was detected, and then we have this Swift string in it. So yep, looks like this is the function responsible for generating the error dialog. Okay, cool. Now what we have to do is to just look from where this Swift UI alert method is being called in order to figure out the function from where Frida is detected. So for that, let's just go at the top of this function in the disassembly and look at its cross references. So there are two cross references for this function. First one is from the get body itself, which is the same function only, and then the other is this, which is this one. Okay, so again it's just a string somewhere defined, but it doesn't exactly resolve from where it's exactly being called. Okay, so let's try to attack it smartly. Going back to the string, it says Frida is detected using socket port or dylib, right? We have already ruled out the option of dylib, so only socket port is the one which is left, which might be detected by this application. And normally what happens is, when Frida server runs, it opens a TCP port by default at 27042. So the app might be listening for this particular port, whether it's active or not. Now, there are very limited functions available which allows you to connect to the port, and these functions are socket and connect. Now, these functions are actually part of system libraries, so they must be present somewhere under the imported sections of the binary. So let's go back to this symbol tree and expand this import section. And there are a lot of imported libraries used by this framework, used by this dynamic library. Let's have a look at this libsystem B, because usually this is the framework or the library, system library, which contains these socket and connect functions. So let's see if we have them over here. And yes, we can see there is this connect function. Yep, the socket function is also there. Cool. So now what we can do is to look for the cross references to either this socket or connect function and figure out in which function these two functions, socket and connect, are being called. Let's click on connect and look for its cross references. And we can see that it's being called from three places. Basically, one is from the data section itself, the other two are these places, and these are the branching instructions. So these two are the places basically from where the connect function is being called. So let's see, let's go to the first branch instruction, and it took us over here under the decompiled code. We can see that it's part of this function canary socket pro. All right, sounds interesting. And inside this function, if you have a look at the decompiled code over here, the first thing we can observe is that there is a Swift string being initialized which says 127.0.0.1, which is nothing but the IP of localhost, right? Then if we scroll down a bit, we have a function called to socket, right? And then a function called to connect. Okay, this looks interesting. So how basically this socket communication works is basically we first have to create a socket and then connect to that particular socket using a specific IP and port. So most likely what is happening over here is here it's trying to create a socket, and once the socket is created, then it's trying to connect to it. And if you have a look at the signature of the connect function, the first argument is basically the socket file descriptor, which we will get as a result of this socket function call. So this ivar3 is the socket file descriptor. Then the second argument is structure of type socket address, which contains three things: length, family, and data. So only this data portion is important for us, because inside this data field only the port is defined, right? And then the third argument is the address length. So the second argument looks interesting. If we are able to parse this second argument, then we can figure out at which port this connect function is trying to connect. And like I mentioned earlier, by default Frida server listens on port 27402, right? So at this point, what we can do is, using Frida, we can try to attach a hook to this connect function and try to pass this second argument to figure out at which port it's trying to connect. Okay, so let me just clear all this thing and go back to the root directory. Yep, and let's create a Frida script using Vim called challenge1.js. Okay, now attaching a hook to a system library is pretty straightforward. All we have to do is call the interceptor.attach API of Frida, and this API takes two arguments. First is the address where you want to attach your hook. In this case, we want to attach the hook on the connect function. In order to get the address of the connect function, we can use module.find global export by name, and here we have to pass in the name of the function. So this followed by function body, where we have two callbacks. One is on enter, which takes args as its argument, and second one is on leave, which takes return value as its argument, right? This on enter callback will be called when the connect function is called, and the on leave function will be called when the connect function is about to return. Now if you remember, the first argument we can access using args0, which is the socket file descriptor, right? And the second argument of the connect function was the socket address, right? And then the third argument of the connect function, which we can access using args2, is socket length. So we are only interested in the second argument of the connect function, which we can access using args1. So let's do that. Let me create a constant variable called socket address and assign args1 to it. Right, so whatever the address where the structure of socket address is present in the memory, that address we now have in this socket address variable. And then, like I said, this socket address basically contains three fields. The data field is the one which contains the port. So I am not going into the details of how you can pass this structure, but if you are interested, you can have a look at this video, hacking C structure, where I have explained how you can navigate or parse through a structure. For now, let me quickly assign the port by parsing this socket address. To the socket address, if I add 2 bytes, I will get the data field. Okay, and then this data field is actually a character arrays, which is in the form of network byte order. So we have to convert it into a host byte order, and for that there is this simple calculation. Okay, then can simply print out the log, which says connect TCP port, right? And on leave callback, let me just put a log to be sure that everything is working as expected, and what's the return value of the connect function. Okay, we can now save this script. So there you have it, challenge1.js. Now before launching it through Frida, let me just enable my virtual environment. Now, before we launch this application via Frida, we must know what its bundle identifier or the package name is. For that, again, we can use a command of Frida called frida-ps-uai, and this will list down all the packages of the application which are installed on your device. We are looking for Frida in the middle, and its package name is listed here, com.8ksec Frida in the middle. Let's just copy this, clear the terminal, and in order to launch the application using Frida, we have frida-u followed by script which is challenge1.js -f to forcefully spawn the application, and then the package name. Let me just bring this over here, shrink it a little bit, hit enter. So as you can see, the application was launched, and in the console our script indeed ran, and in the logs it says connect TCP port 27042, and the return value is 0, which means success. So this confirms our hypothesis that connect function is indeed being used to detect the Frida server port. Now, there are two ways in which we can bypass this detection mechanism. One is if somehow we manipulate this TCP port from 27042 to something else, this detection might be bypassed. Another way is to modify the return value and return something else instead of 0. So let me just show you the first way, because that is most accurate way in which you can bypass this detection. So again, let's open the script challenge1.js, and inside this, after we got our port, let's put a check. If the port we have extracted is equal to 27042, then only we will do something, otherwise we will just skip it. Okay, so inside this port, I'm going to put a log which says by passing Frida port check. This will be useful for troubleshooting or debugging if required. Then let me create a temporary variable where I'm going to modify this 27042 port 243. And to do that, all we have to do is perform some shift operations. So here basically I am modifying the port value from 27042 to 27043, right? I'm not going to dive deep into how this operation is working and what's happening in the memory, because that will be too much information. But let's say if you, instead of 27043, you want to modify it to some other port, all you have to do is replace this 27043 to that particular port. Okay, so this is done. Then all we have to do is modify the data field inside the socket address structure, right? If we add 2 bytes to the socket address, we will be at the data field, right? Just like we did over here. And this time, instead of reading, we are going to use the write method. And here I'm going to put temp value. Let me just store it again back to the port variable. So now if you have a look at this port variable, it will be having 27043 instead of 27042. So now when this port will be printed at runtime in the log, it should contain 27043. And because 27043 port is not running, the return value should be something else instead of 0. Okay, that's all. Let's save this script and launch it one more time. Enter, and yep, awesome. You can see that we are inside our if condition where we have printed by passing Frida port check. Inside the TCP port, okay, it printed out the address where the port variable is present, but that's okay. And the return value is changed to FFFFF, which means -1, which says that connection to the port is failed. Okay, so that's all what we wanted. And in the application also, you can now observe that we are not getting that Frida detected error message anymore. So we have successfully managed to bypass the Frida detection. Here now it says no Frida activity detected. All right, awesome. So the first step is done. Now the second step is to figure out where this dummy function is present and attach a hook to it to print its first argument, right? So let's go back to Ghidra and have a look at the functions. Okay, so it's hard to locate it manually. What we can do is we can filter it out. Type dummy function, and yep, there you go. Here it resolved the dummy function for us. This is basically the internal function Frida in the middle content view dummy function flag, and this underscore dollar s16 whatever this encoding you are seeing is basically happened because of a technique called symbol mangling. So what happens is when you compile or build a Swift application, the compiler mangles the symbol names and introduces this kind of encoding. Okay, but still it's pretty straightforward to figure out the function name and the class and the package, right? So now we have spotted the function, which is this one dummy function. And in the decompiled code, you can see that this function is doing nothing. It's simply returning something, but its first argument is of type string flag. And this is exactly what we want to extract. Again, you can spend some time to do the static analysis of this dummy function, like from where it is being called, what argument is being passed statically. But again, that is not the objective here. The objective is to hook this dummy function, and for that we have to figure out its address, where it is located, and the address, or actually not the address but the offset where this dummy function is located is 5D24, right? So we have to add the actual base address of this dynamic library in order to figure out the exact address of this function in the memory, and then only we will be able to hook this function. So for now, let me just copy this offset and go back to the terminal, clear the terminal and go back to the script. Now let's leave this connect hook as it is, and then I'm gonna attach a hook to this offset. But before that, I am going to find out the address where this dynamic library is loaded in the memory. So in order to figure out the base address where this module is loaded, again we are going to use the API of Frida called process dot find module by name, and the name of the binary is Frida in the middle dot debug dot dylib. So this will give us the base address where the dynamic library is loaded, and let's store it under a variable called module. And again, for troubleshooting purposes, I am going to print this base address. So module dot name is loaded at module dot base. All right. Now, as you know, to attach the hook, we have intercept dot attach API, right? Just like what we did for connect function, but this time instead of using the module dot find global export by name, because we now dealing with the address, what we have to do is take the base address of this module using module dot base and then add the offset where the dummy function is located, which is 5D24, right? Followed by the body of the function, which takes two argument on enter and on leave, but this time I'm not going to bother about the on leave. So let me just define the on enter callback, inside which we can get the flag in the first argument, which we can access using args0. And because it's of type string, we can use read c string to read it in the string form. Dummy function flag value of the flag. That's it. Let's save the script and let's launch it one more time. Alright, Frida is bypassed, and now if we click on this intercept first argument, we got an error which says access violation accessing this address. Alright, okay, I know why this is happening. We just close this. So this is happening because in a Swift based application, the string is actually not a string. Swift has a different representation of string in memory. So we have to first cast it into a proper format. For that, actually, some people have already raised some issues in Frida repository itself. And one such issue I found was this one, where the guy is exactly looking for the same thing we are looking for, which is how to parse Swift string value. And if you scroll down to the bottom, you will find the solution as well, which is this one. So here basically what this guy has proposed is, inside this Swift Foundation library, there is a method called bridge to Objective C to NS string. What this will do is basically it will convert the Swift string data type to the literal string form. Okay, and inside Swift memory representation of string, it requires the address of the string and the length or the size of the string. So that's why we need two arguments to resolve this string properly. Okay, simple. So all you have to do is copy this code, go back to the terminal, clear it out, open the challenge script inside our hook, or okay, before our hook actually, we have to paste this code, and now inside the interceptor dot attach, instead of reading it in the form of C string, what we have to do is simply call this create swift string method. As I explained, it takes two arguments, right? First argument has to be the 0th index, and the second argument should be args1. And launch it one more time, enter. Let's click on intercept first argument. Okay, looks like something is not right in the script. Let me go back. Okay, yeah, I know. So basically in the newer versions of Frida, we actually don't have this find export by name API anymore. It's actually find global export by name. And now we don't have to mention the name of the target library. All we have to pass is the name of the symbol. Clear, launch it one more time. All right, click on intercept, and there you go. Dummy function flag is called, and the flag is CTF you evaded Frida detection. Awesome. So that's it for this challenge. Pretty simple, but definitely fun to work on. I would say the only tricky part here was to figure out how to properly resolve and parse a Swift string. Okay, if you found this helpful, let me know in the comments. And the upcoming challenges are going to get progressively harder, so get ready for that. And of course, don't forget to like, share, and subscribe. I will catch you in the next video.